Excellent. 3.4 physics lesson. Last one in this chapter. We're almost through it. Okay. Displacement with changing velocity. So initially, we have these equations. We have our displacement, we have our average velocity, and last at the beginning of 3.1, I kind of threw in this acceleration, right? Now this is all great, but now what we have is a changing velocity. So this equation right here, our average velocity equation, we can only use that now if we have a constant velocity. If velocity is not constant, we can't use it. We have to use something different. So I have these equations here for you. These are three of many equations that you'll get in physics, but these ones are very, very helpful in this unit and units to come. So what they do is they relate this displacement with our changing velocity. All right, so this first one, this is a good equation to use whenever we don't have A given. So we're getting a problem, you don't have acceleration given. Hey, what you can do is you can use this. As long as you have delta x, or you're looking for delta x, and you have VF, VI, and T. Don't ever try to solve an equation if you have more than one unknown variable, at least in this class, because that gets a little bit intense algebraically. All right, this next equation, not equation, although sometimes I do question myself. Anyways, so this one right here, you might notice that it's missing a VF, so the velocity final. So this works really good if you don't know how fast or at what velocity an object is traveling after a certain amount of time, and you can figure out how far away it is. Now, I will stress on this one, there is two spots for time here, and they do not cancel each other out in normal fashion. So if you're looking for time and you have everything else, but you're just looking for t, I wouldn't use this equation unless you really want to use the quadratic formula, because that's what you're going to end up using. All right, this last one here, this one is awesome. It's going to be your go-to. This works great if you don't have time given. So you're like, whoa, why would I ever use this? Well, this is going to be great, again, if you don't have time, because the other two equations have time already built in. And you can also use this as a workaround if you need to solve for time later on. You can solve for VF, you can solve for VI, whatever you need to solve for, and then plug it in into a smaller equation that has time with just one variable. Also, if you go back over here, you can look, and if you solve for VF and VI and you have acceleration, hey, look, there's time again that you can solve for. So this equation is very useful all the way around. So let's see how some of these would work. This video might go a little bit longer because I'm probably going to go through all of these practice problems, so hopefully they don't cut me off. All right, so we have a skateboarder, and she's going down a ramp at 5 meters per second. So velocity initial is negative 5 meters per second. After 5 seconds, so time equals 5 seconds, she is traveling down at 15 meters per second. So velocity final equals 15 meters per second. How far down did she get? Delta x. Now, when you are starting at a initial position that is 0, and you're only moving in one direction, forward, backwards, whatever, then your distance and your displacement are the same. However, that's not always the case. So in these situations, they will be, but be careful, especially on their homework. There's one about Boris, and Boris is this, crazy flying insect that has all kinds of superpowers, and he can actually be invisible and stuff. But anyways, Boris is not going to start at 0. He starts at like 240 or something like that. So if you're watching this for my class, which you probably are, keep that in mind. The initial position is not always 0. So how can we solve this? Well, we're going to use that first equation that I gave you. So delta x equals 1/2 velocity final plus velocity initial over time. Why am I picking that equation? Because I have all these variables. I have velocity final. I have velocity initial. I have time. So I have everything in here. that I could use to solve for delta x. So 1/2, no, it's negative by the way, negative 20 meters per second times 5 seconds should give you negative 50 meters, right? So half of negative 20 is negative 10. Negative 10 times 5 is negative 50. Or you could just put 50 meters down. Problem number 2. Now we have a motorcycle, and we're driving at 24 meters per second. So velocity initial is 24 meters per second. The motorcycle is going to slow down at an acceleration of negative 3 meters per second squared for 5 seconds. Awesome. So we're not given how far, because that's what we're looking for, but we're also not given velocity final. So velocity final, not given or no good. So you can use that next equation that we had on the slide previous. 1/2 a t squared plus vi times t equals delta x. So 1/2 of our negative 3 times squared. Be careful. A lot of kids, a lot of students, a lot of adults forget to use the square. It has to include the square. Plus velocity initial, which is 24, times the time, which is 5. Now, another thing to make sure is don't forget the negative sign. So the square is important to remember, but so is the negative sign. If you don't forget the negative sign, you're going to end up with a bigger number than the answer, and the answer should be 82.5 meters. So that's how far down the ramp we should get. All right, last one. Roy rolls a ball up a ramp at 15 meters per second. Velocity initial is 15 meters per second. The hill gives the ball an acceleration of negative. Well, yeah, because gravity sucks. So acceleration is negative 3 meters per second. How far will the ball make it up the hill before it begins to roll back down? So be careful with this one. How far does it make it up the hill before it begins to roll back down? So the maximum height should be where the velocity final is 0. Now, picture it like this. Here's your ramp. The ball's going this way. If it didn't change direction, it would fall off the ramp. So somewhere in this area, it has to stop and come back the other way. So, how are we going to figure that out? This delta x. Well, that goes to that last equation that could look a little intimidating. So, last equation was 2 times negative 3 delta x equals velocity final squared, so 0 squared, minus 15 squared. Now, one other thing I'd like to point out about when you're using this equation is if your velocity initial is negative, so let's say it's a negative 15 instead of a positive 15, you want to take the square first. Order of operations says you take the square first. And calculators are dumb, and you're not. You take negative 5 and multiply it by negative 5, you get a positive 25. But the calculator, if you put in negative 5 and you try to just push the square button, what it'll do is it'll do the 5 squared and then add on the negative. So be careful, because you're smart and calculators are dumb. Anyways, the distance displacement ends up being 37.5. All right, hopefully this wasn't too long. Thank you for tuning in, and I will see you in Chapter 4.